Well, we've talked about the principal quantum number n and the angular momentum quantum number L. Let us move on into the world of the magnetic quantum number. What is its symbol? What does it tell us about the electron? And what are its values? So let us go back to our beautiful concept map. And let's go into the green zone with the magnetic quantum number. What does this tell us, first of all? Well, excuse me, what is its symbol? Its symbol is M. All right, piece of cake, M, magnetic. That's an easy one to remember. Good. Now, what does it tell us about the orbital? In this case, remember, first of all, N told us about the energy level, which is the distance from the nucleus of the electron. L told us about the shape of the orbital, and M tells us about the orientation of the orbital in three-dimensional space. And what does that mean, really? Hey, in these cases where I have p orbitals or d orbitals, what direction is it? Is it going to be in the x direction? Is it going to be in the y direction? Is it going to be in a z direction? That's all M is telling us. It tells me how my different orbitals are aligned in space, okay? And that's a beautiful picture. Good. So I think, oh, values. We need to talk about the values for my M. M is easy. M is plus or minus, excuse me, let's start off with all integers between and including negative L and positive L, including 0. So let's write it this way. M is negative L, sorry, let's write it that way. Well, I guess positive on this side, right? And negative L, including 0. So these are my values. All integers, let's make sure we write the word integers from minus L to positive L, including 0. All right, so here we go. Let's see if we can answer our question. Oops, let's see if we can answer our question. Yeah. We'll go to the pink purple. Okay, what is its symbol? The symbol for the magnetic quantum number is M. Good. What does this indicate about the orbital? It tells me its orientation in space. Orientation in space of orbital in space. You don't really have to say space. Orientation of orbital would be sufficient, right? And what are its values for L? Now, what did we say? We said that its values are greater than and equal to minus L and less than and equal to positive L, and we want to include 0. Okay, so here we go. L is equal to 2. That means what? My M's, I have a whole bunch of M's here. M's are equal to negative 2, negative 1, 0, 1, 2, right? So for one single value of L, I have, in this case, 5 M's. Now, what does that mean? Well, what does L equals 2 mean to us? L equals 2 means what? L equals 0, 1, 2, SPD. So we're talking about a d orbital. And for that shape, how many M's? M's means what? Orientations. So my L2, that means I have a D shape. And how many orientations do I have? I have 5 different orientations. And so this is how we get our numbers, right? If I have an S orbital, how many orientations do I have? I have 1, so that means I have 1s. When I have a p orbital, I have how many orientations? Well, it turns out it's going to be 3. When I have d orbital, how many orientations? Well, I have 5. And that's how we end up getting those number of orbitals in that table we are looking at. When L is equal to 3, I have F. How many different M values am I going to have? 7. So I have 7 different orientations of an F, meaning I have 7 different F orbitals at that energy level. All right, here you go. Let's see if you can do this on your own. L equals 3. What are the values for M? How many orientations of the orbital exist at L equals 3? Here we go. Pause me and unpause me when you're ready. Okay, what are the values for M? Well, L is equal to 3, so that means I'm going to go from -3 to +3, including 0. So that would be -3, -2, -1, 0, 1, 2, 3. So those are my values. How many different orientations do I have? I have 1, 2, 3, 4. Notice 0 represents an orientation. It does not mean 0. 1, 2, 3, 4, 5, 6, 7. I have 7 different orientations for the orbital at L equals 3. Yahoo! Okay, here we go. The 4s orbital, how many values of M exist for this orbital? All right, I'll give you some time to do this. Unpause me when you're ready for the answer. Okay, 4s. So what does that mean? That means my N is equal to 4. My S, that means my L is equal to what? Okay, I always have to write this down because I sometimes get confused. L, excuse me. Yeah, L, that's right. L in my shape. Good. L always starts with what? 0, 1, 2, 3. My shapes always start with sphere, S, P, D, F, right? They're always in this order. 0, 1, 2, 3, S, P, D, F. And if I just wanted to know the number, I could always remember it's 1, 3, 5, 7 of these orbitals at that energy level. Good. So when I have an s orbital, what's my L equal to? My L is equal to 0. Good. Now, how many values of M do I have for this? Well, I go from -L to +L, including 0. My L is equal to 0. So 0, 0. So what do I have? I need M between 0 and 0, including 0. So what does that mean? 0. So what is the value? Remember, 0 has meaning in quantum numbers. What is the value of M? The value for M the value of M is 0 for 4s, right? And how many orientations are there for this? Well, I have one value of M, so how many orientations do I have? I have one orientation because the value of 0 is still an orientation. Yeah, I know that kind of blows your mind mathematically, but remember, quantum numbers are less about math and more about symbols. All right, finally, the last one, the spin quantum number. That is great. Okay, what is its symbol and what does it indicate and what are its possible values? All right, this is the last quantum number. Let's go to our concept map and let's finish that off. We're into the blue zone here. Okay, what is its symbol? The symbol is a big S. Now, what does it tell me? It tells me the spin of the electron. Good. So the spin of the electron, and what are its values? It is a positive 1/2 and a negative 1/2 for every value of M. So if M is -1, then my S is equal to +1/2 and -1/2. If my M is equal to 2 +2, let's make that M, it's still, I have an S that's associated with that equal to +1/2 and -1/2. And that sounds a little confusing, and it will become very clear here in one moment. Good. So the spin quantum number, what is the symbol? S. What does it indicate? Spin of the electron. And what are its possible values? -1/2 and +1/2 for every value of M. All right, great, here we go. An electron with an M of -3. What are the possible values of S? Easy. So M is -3. So what are my S's? Well, for this, I can have a +1/2 and I can have a negative 1/2. There we go. That is the answer. Now, think about this. Well, we won't think about it just yet. All right, the quantum number. Sorry, went too far. The quantum number. This is it. The quantum number 2, 1, negative 1, 1/2 is a valid Is this a valid quantum number? 2, negative 1, negative 1, 1/2. Well, we have to start from the top. So let us summarize here. What are my values? What are my possible values for n? N can be 0, 1, 2, 3, right? L, what are my possible values for L? Well, everything from 0 to n minus 1. Good. What are my possible values for M? Well, my M values are negative L to positive L, including 0. And what are my values for S? Positive 1/2 and negative 1/2. Okay, so here we go. I have, and the way to read this is, this means this is a quantum number. This is N, L, M, S. There we go. These from left to right, they represent N, L, M, and S. Good. So this means I have N equals 2. Okay, so here we go. N equals 2. So what are my values for L? Well, I have a whole bunch of values for L. In fact, how many values for L should I have? Well, N is equal to 2, so I have 2 values for L. I start at 0 and go to n minus 1. 2 minus 1 is 1. So I'm going from 0 to 1. So my values for L are 0 and 1. Good. My values for M, well, for every one of these L's, I have a set of values of M. When L is 0, that means I go from 0 to 0, then my M is 0. When L is equal to 1, however, let's think about this. L equals 1, then that means I'm going from negative 1 to positive 1, including 0. So how many values of M do I have for 1? I have 3, and they are negative 1, 0, and 1. Wait. Hold it. Look at, hey, there's a 0 here and a 0 there, Mr. Smith. Why? That's got to be wrong. No. It's right, because this 0 is associated with which L? It's associated with the 0L. And remember, what does 0L mean? That means I have a sphere, right? So this means this is the orientation for the sphere. Well, what about this 0? Well, this 0 is associated with a different L. L equals 1 is what kind of an orbital? It's a p orbital. So this 0 is telling me something about this p orbital. So it is not the same as this 0. These are two different zeros, and we have to write them down twice because they represent two different things. Good. So now we add our s's. I have a 0 here. How many s's do I need? I need a plus 1/2 and a minus 1/2. I have a minus 1 here. How many s's does it need? A plus 1/2 and a minus 1/2. I have a 0 here, plus 1/2, minus 1/2. I have another m here, plus 1/2 and minus 1/2. Okay, so now these represent my quantum numbers associated with n. N equals what? N equals 2. N equals 2. Good. So this would represent one entire, this shows us all the possible quantum numbers at n equals 2. Now wait a minute, time out. Quantum numbers tell us about electrons, right? N tells me the number of electrons I could have. Remember that? We said what? Number of electrons equal 2n squared, right? Okay, so I have n equals 2, right? So that means I'd have 2n squared, 2 squared, 4, 8. So that means I have 8 electrons at the n equals 2 level, at n equals 2. That means I should have 8 quantum numbers describing each of those electrons. Do I? Yes, I do. Now here's how that works. I take my N, I take my L, I take one M, and I take one S, and I write out the number. So I start up here, right? And I'm going to go 2, comma, then I go down here, 0, comma, and then I go down here, 0, comma, and then I go down here, plus 1 half, oh, plus 1 half. And then I have that same thing again, right? 2, comma, 0, comma, 0, comma, but instead of plus 1 half, I have minus 1 half. Okay, so this represents 1 electron, 2 electrons. Now I go to N again is 2. But then I don't go to 0, I go to L equals 1. So I N, 1, and then from there I go to minus 1. And then I go from there to plus 1 half, 2, 1, minus 1, minus 1 half. Then I go 2, 1, 0, 2, 1, 0. And then from the 0 to the plus 1 half. And then 2, 1, 0, minus 1 half. And then finally I go from 2 to 1 to positive 1, 2, 1, 1, plus 1 half, and 2, 1, 1, minus 1 half. Wow, that seems hard, Mr. Smith. Well, you know, if you do it in your head, it is hard. But if you write out this kind of chart, this kind of matrix, it's a piece of cake. And we'll write that out again in just a second. Now, did we answer our question? Is it possible to have 2, 1, minus 1, 1 half? Let's see. 2, okay, all these are 2. 1, okay, 2, 1. We're looking at these two right here. Minus 1, yes, positive 1 half. 2, 1, minus 1, 1 half. Is that possible? The answer is yes, it is possible. Okay, good. Quantum number 3, 1, minus 2, negative 1 half. Okay, here we go. I'll give you a few seconds to do this. Pause me, and when you're done, let's do this together. All right, here we go. N equals 3. If N equals 3, what are my possibilities for L? Well, L can be 0, 1, 2. That's great. Now, what are my possibilities for M? Well, for M equals 0, and let's give me some more space here. Let's do it this way. 0, 1, 2, because we're going to need space. What are my possibilities for M? Well, when L is 0, we said M is equal to what? Negative L to positive L including 0. Well, that's 0 to 0 including 0. That means it's 0. What are my values for L equals 1? Negative 1, 0, 1. What are my values for M equals, or L equals 2? Negative 2, negative 1, 0, 1, 2. What are my values for S? That's easy, right? 1 half, positive 1 half, negative 1 half. 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 All those are positive 1 halves, all those are negative 1 halves, okay? Good. So you just pretend these are all positive 1 halves, negative 1 halves. Okay, so let's go. 3. Do we have 3? Yes. Do we have a 1? Yes. 3, 1. Good. Under my 1, do I have a negative 2? Under my 1, do I have a negative 2? Well, I have a negative 2 over here, but where is it? It's under my 2. Do I have a negative 2 under my L equals 1? The answer is no. No. I can only have what? For L equals 1, I can only have M equal negative 1, 0, and 1. Remember? Negative L to positive L, including 0. So I do not have a negative 2. That means this is not a valid quantum number. End of game. All right, here we go. Let's do this, and this is the biggie. Let's create the first 3 electron shells, and we're going to list all the quantum numbers. Well, let me see how much time we have. All right, we have plenty of time. Good. Let's just make the matrix. The matrix for the first 3 quantum numbers. Our first 3 shells. That means, hey, shell means what? N. So we'll write N over here, and we'll go N equals 1, N equals 2, and N equals 3. Ooh, baby. We're going to need lots of space. I'm going to have to write small. I'll tell you what, I'm going to do this sideways so we have plenty of space. I'm going to switch this on its ear. So we're going to say this is my N. Here's my N. Here's my L. And here's my M. And here are my S's. Good. So N equals 1. When N equals 1, what's my L equal to? Okay, okay. Maybe we should, before we go any farther, let's even get rid of this and let's do our quick summary. Okay, N is positive integers. That means 1, 2, 3, and so forth. L is what? L is 0 to N minus 1. Good. M, what does M equal to? Negative L to positive L, including 0. And what does S equal to? Positive 1/2, negative 1/2 for every M. Okay, now that's kind of our summary. Let's do this. Here's M, here are my L's, here are my M's, and here's my S. N equals 1. When N is 1, L is equal to what? Let's put it up. L is equal to what? 0 to N minus 1. 1 minus 1 is 0, so L is 0. When L is 0, M is 0, and then I would have a positive 1/2 and a negative 1/2 associated with this, right? Good. N equals 2. N equals 2. What are my values for L? Well, I'm going to go from 0 to N minus 1. 2 minus 1 is equal to 1. So I'm going from 0 to 1. So there's a 0 and there's a 1. Now, what is my M when L is 0? That's easy. That's 0. What is my M when L is equal to 1? Let's extend the page. We're going to need more space. Can you believe that? More space? Yes, more space. It's negative 1. I go from what? Negative L to positive L for my N. M. So negative 1, 0, positive 1. This becomes positive 1/2, negative 1/2, positive 1/2, negative 1/2, positive 1/2, negative 1/2, positive 1/2, negative 1/2. Good. Okay, so we're through 2. Now the biggie, 3. When N equals 3, what are my values for L? I think we're starting to see a pattern. 0, 1, 2. Good. What are my M's? Well, when L is 0, M is 0. Good. When L is 1, M is negative 1, 0, positive 1. When M is 2, when L is 2, what do I get? Negative 2, negative 1, 0, positive 1, positive 2. Woo, baby. And then what do I have to do? Oops. All my S's. 1/2 minus 1/2. Oops. 1/2 minus 1/2. 1/2 minus 1/2. And so forth. Okay, all the way down, I'm assuming 1/2 minus 1/2. 1/2 minus 1/2. 1/2 minus 1/2, right? Wow! Well, that is it. Those are your quantum numbers. That's how we create our quantum numbers, right? And so it would be something like 1, 0, 0, 1/2, right? Or here we'd be having what? For this area right here, it would be 2, 1, 0, 1/2, right? Or 2, 1, 0, negative 1/2. Down here, the 4 quantum numbers. Let's go this way. You won't, right? Oops, right here, got to include my N equals 3. 3, 2, negative 2, 1/2. Got it? Does that make sense to you? All right. Yeah, because here's my 3 zone. Here's my 3 zone. And here's my 2 zone. And here's my 1 zone. And this is what we call what? N equals 1. So what is this? This is my first shell. This is 2, so this is my second shell. N equals 3. So that would be my third shell. Cool. Good, good. How much time do we have left? Well, I better call it off. Well, one last thing. No, I guess we better call it off. All right. So that would be it for quantum numbers. You are now a quantum number expert. Good luck. Let me know if you need some help. Bye-bye.